So hi everyone, thank you for coming. I am Lydia from UC Berkeley, and I'm a second-year PhD student working on machine learning optimization, and I'm going to be talking about one of our recent papers on the delayed impact of fair machine learning. So this is joint work with my colleagues at Berkeley. And so if you came to this talk, I'm thinking that you might have one of the following two questions on your mind. So one is like, what is fair machine learning? What is she going to talk about? And maybe two is, if there is such a thing as fair machine learning, how do I make sure that the algorithms I'm deploying in my enterprise or in my work are fair? So in the machine learning community today, both these questions are matters of active research. So the bottom line is there's no one-size-fits-all solution that's going to manage fairness or the risk of having bias impact. So instead of this, I'm going to introduce the ongoing conversation in the fairness community through the lens of our recent work. And I'm going to hopefully suggest some ways of thinking about how to audit these fairness criteria and audit your machine learning algorithms using a domain-specific approach, something that fits to your particular application. So if we look at the history of fairness research in machine learning, it is actually somewhat a recent phenomenon. It's not something you traditionally hear people talk about. And it also almost came sort of as an afterthought to like all the success in machine learning. Suddenly people are finding lots of examples where you apply an algorithm to something and it seems to be discriminating on the basis of some attributes such as race or gender. So this has led to a lot of recent work in machine learning. It has grown sort of almost exponentially. And this year as well, there are lots of researchers working on this topic. It's gone through the roof. And in particular, there was a tutorial earlier this year by Arvind Narayana of Princeton University, where he talked about the 21 definitions of fairness. So there isn't just one way to describe fairness mathematically. There are 21 possible ways. And now that we have all these ways to formally talk about notions of fairness, then the question is, what can we do with all these definitions, right? So in fairness, there is this notion of a protected group, which is usually like a gender group or race group or socioeconomic status group. And a lot of work in algorithmic fairness have this implicit assumption that by applying a fairness criteria, you're going to make the protected group better off in some sense. Or at least you're trying to protect them from the harmful outcomes of algorithmic discrimination, for example. And the justification for this is curiously left to intuition. So in our work, we critically examine whether this implication is the case using a model. So let's first explore this question here with an example. So here I'm showing you like the credit scores, this credit score histograms for two different groups, which could stand in for two different genders or two different race, age groups, whatever you want. And so you have the blue group and the orange group. And so if we think about credit scores, we know that higher credit scores imply at that score, like a greater proportion of people repay their loans. So it's like a higher likelihood of repayment. And so the people who would repay their loans at each score is indicated by the empty circles. And those people the people who would not repay is indicated by the empty circles. And people who would repay are indicated by the solid circles. So the bank does not know a priori who would or would not repay, but they know that at a particular score, there's a particular proportion of people who will repay their loans, right? And in this case, the blue group has lower scores on average, and we could think of them as the protected group or a disadvantaged group. And the bank would like to know how to give out loans to these two groups, given that it also cares about being fair to both these two groups. So one fairness criteria that people commonly use is called demographic parity, and that means that in both groups we give loans to the same proportion of people. So that leads to two different thresholds for the two groups. And the thresholds guarantee that the people we give loans to, the fraction in the blue group is the same fraction as the orange group. And so now after the individuals gets a loan, according to this policy, they could repay they could default. So if they repaid their loan, their credit scores will increase. And if they defaulted on the loans, then the credit scores will decrease, right? And the interesting thing that has happened here is that in the blue group, more people defaulted than they repaid. And in the orange group, everyone repaid, and the scores all moved up, right? So we can actually say that in the blue group, the scores got worse on average, and in the orange group, the scores got better on average. So there's something strange happening here. We apply a fairness criteria in hopes of doing good by the blue group, but in the end, their scores got worse on average. So when this is like a harm to the blue group, because that means in the future they have more debt and they also have less access to credit with these like worse credit scores. So what I showed you with this example, right, is that once we consider the impact of loans on scores, like in the next time period, it's not clear that the fairness criteria is helping the group. In fact, they did not help the protected group. So this motivates us to study more generally what is the delayed impact of running these classification algorithms. So in our work, we first introduced a tool called the outcome curve that allows us to compare the delayed impact of fairness criteria. So it is what we did just now using that simple example, but in a more systematic way. And with this tool, we're able to provide a complete characterization of the delayed impact of 3 different fairness criteria in the model. And with this, we show that the fairness constraints may sometimes cause harm to the groups that they intended to protect. So before I get into the results, I just set up the problem with some definitions. So we already saw what a score is. So just to put it a little more formally, it's a random variable that's a scalar, it's like a scalar value, random variable, and it's a function of an individual's features. So we can just think of this score as coming from some machine learning algorithm, like a FICO credit score, or you train a model to come up with a score. And for example, the credit score is this integer value, and it has already, is a function that has already taken in the individual's features, such as their financial history, such as their maybe some demographic information, and it just comes up with a value that tells you what is the probability of repayment, how the credit worthiness, for example. So if one individual has a single credit score, and then any group of individuals has a particular distribution over scores. So this is the histogram, again, is telling us that at each score, what's the proportion of people in the population who have that score. And so the main assumption we have to make about the score is just that the individual success probability and the score correspond to each other. So with higher scores, there's a higher probability of success. So in the credit running example, that means higher credit scores means more likely to repay, which is completely intuitive in this case. So we call this the monotonicity assumption. And once we have these scores, so the bank would want to use these scores in some way. So the most general way to use the scores is by choosing an acceptance threshold. So above that threshold, they would loan to the individual. Below that threshold, they will not approve the loan. And how do they choose this threshold score? It's by maximizing their own utility, which in the case of the bank is by maximizing their profit. So the profit, the expected profit from choosing a particular threshold, it consists of 2 terms. So one is the first term, the expected reward from people who will repay their loans. And we have to subtract from that the loss from the defaults. So you have to take into account what happens if they repay their loans and what happens if they didn't repay their loans. And you are averaging over the randomness in the repayment default events. So for any single group distribution, if I choose a particular threshold, that means I accept a proportion of the population. And that proportion, I call it the acceptance rate. Right? For example, if I accept 20% of the population by only giving out loans to people above credit score 800, for example. So there is this one-to-one correspondence between the threshold and the acceptance rate for any single group. And then when there are multiple groups, the thresholds can actually be different for different groups. And this is something that is necessarily enforced by using some of the fairness criteria. So here you can see I'm using different thresholds for the two different groups. So now that you decide on the policy, whether to loan or not, the scores of the individuals who are accepted actually change depending on their success. So if the scores will increase for someone who repaid their loans, and it will decrease for someone who defaulted. And if you don't get a loan, then your score just doesn't change, right? So in this case, because the individuals experience some kind of change, then over the whole population, the population also experiences a change in the distribution of their credit scores. And how do we measure this change? So one very obvious way is just to look at the average change in that group. So we just call this average change the delayed impact. So it's the expected future score minus the previous score. So it's just the expected change in score. And this is the key quantity that we'll be studying in this talk. So now that we have defined the delayed impact, we can look at how the delayed impact changes with the acceptance rate. So under very general conditions, we can basically show that the delayed impact is this concave function as we increase the acceptance rate from 0 to 1. So the way to think about it is just when you increase your acceptance rate from the beginning, people's delayed impact starts improving very rapidly. Eventually, it reaches a maximum, and then it goes down. That's the story of this curve, but we can go through it more slowly. So what's happening on the x-axis is just the bank's acceptance rate for a particular group. So if the bank gives out loans to everybody, that's acceptance rate of 1. If the bank doesn't give out any loans, it's an acceptance rate of 0. So there's effectively no bank, right, in this case. And then there is no effect on people's average score in that group. So that's just at 0, 0. And then if the bank wants to start giving out some loans, a natural strategy would be to maximize their own profit. So that's the acceptance rate at bank's utility maximization. And notice that is not the same thing as the point that maximizes the delayed impact. It's just the bank maximizing its own profit. And so if the bank wants to give out loans up to this point, we say that there is, if you give out loans that is less, at a rate that's less than utility maximization, we call that relative harm, because you are benefiting the group by less than what would have happened with just utility maximization, right? So what the bank can do here is to actually start giving out a few more loans to people who can repay them, but they would otherwise not get approved loans for because they want to maximize their profit. So these are people who are still likely to repay, but the bank under utility maximization wants to avoid giving loans to them, right? And if we exchange some profit, so we are willing to lose some profit to give these people loans, then we'll actually still see the delayed impact improve in this regime. So this, we call this relative improvement because the group's credit scores on average improve over utility maximization. And then this eventually we reach this point called the philanthropic optimal, which is the acceptance rate that maximizes the group's delayed impact, right? And then as you continue, somehow you have to start giving out loans to people who are less and less likely to repay. And then more of these loans become end up in defaults, and then that pulls down the average score change again. And so eventually you reach a point where you're again doing worse than utility maximization. And then finally, something really bad starts to happen. You start giving out loans to many people who default, and then the group average score change becomes negative. So that's what happened in the first example I showed you. And this is we just call this the active harm regime. So what I've shown you with this outcome curve is that there are three sort of regimes of interest for us, like relative improvement of the delayed impact over utility maximization, relative harm, so doing worse than utility maximization, and active harm, which is just doing worse than doing nothing. So now the question is, if we applied fairness criteria, where will it put us on this curve, right? Are there situations where it's more likely to lead to improvement, and are there situations that's more likely to lead to harm? So let's, before we go into that, I'll just review, or I'll talk about what are the fairness constraints that we'll be looking at today. So instead of, so utility maximization is just an unconstrained optimization problem. We just want to maximize profit. But what the fairness constraints does is it forces you to also satisfy certain parity constraints. So in demographic parity, it forces you to select the same, have the same acceptance rate for both groups. So if we look at the orange dots and the blue dots, all of them, I want to make sure I want to make sure that the fraction of blue dots I'm selecting is the same as the fraction of orange dots I'm selecting. Another fairness criteria is called equal opportunity. So it's also a parity constraint, but it's different. So this time we only look at the solid dots. We only look at the people who would repay, and we want to make sure that within this, within the solid dots, we're selecting the same fraction of people. And this is called equal true positive rates. The reason it's called equal true positive rates is because those people that we select, so those things in the gray sort of polygons, those are the positives. And then if they're also a solid dot and they're also selected, that's a true positive, right? So that means they actually repaid their loans and they were also granted a loan. Those are true positives. And that's by equating the fraction of solid dots we select, that's equalizing the true positive rates. So we could apply these fairness constraints, which means we would maximize utility subject to these constraints. Now, so in the first result we have, it is that both these fairness criteria can put us anywhere on the outcome curve. So the equal opportunity fairness criteria, as well as demographic parity, they may cause improvement, they may also cause harm or active harm. So all these regimes are possible. And on the other hand, if I just apply unconstrained utility maximization, that never causes active harm. So this beta max util, the way I drew it, it is always going to lie on the left of the active harm threshold beta naught. So this is like a general fact. And the reason for this, the intuitive reason for this is because banks or institutions, we assume that they are more risk averse. So they would stop giving out loans before they would cut off their threshold for giving loans before even reaching someone who has like a 50% chance of repayment, because we want to maximize profit, and that makes them more conservative. So in this case, you can see that by applying a fairness criteria without looking at the particular situation you don't actually know if your fairness criteria is going to give you harm improvement or whatever. And sometimes we can also say things that are more fine-grained, which is what happens when I try to compare two different fairness criteria. So in the second result, we're saying here that demographic parity, the one that equalizes acceptance rates, tends to over-accept. So it tends to land you in the harm regime by accepting too many people. So in a sense, it would force you to give out a lot of bad loans if you want to satisfy this fairness criteria. Whereas equal opportunity does not over-accept. in this class of situations. So on the other hand, something else could happen, which is equal opportunity could under-accept. So it could be like more conservative than utility maximization in some situations. And some of these situations might be due to like in-group inequality, and we have some details in our paper. But this is another class of situations where applying this fairness criteria would be bad, and it would be worse than not applying any fairness criteria at all. Whereas if you apply demographic parity, it would actually be good. So what we're trying to say here is the choice of fairness criteria can really have very different impact on the users or on the stakeholders in this problem. So another situation that might come up in sort of the banking application or other applications is, what if there was some error in the way we measure our scores? So another kind of commonly encountered situation is you get the scores, but you're not sure that the scores really correspond to the true repayment ability. So here, what we mean by measurement error is when the bank systematically underestimates the repayment ability of the disadvantaged group. So to give an example, maybe the bank thinks that a credit score of 700 means you have a 0.8 probability of repaying the loan. So in the orange group, you have someone who has a 0.8 probability of repaying the loan. They actually have a credit score of 700. So what the bank thinks and what is the truth is the same. But in the blue group, for example, there's someone with a 0.8 probability of repaying the loan, but the bank doesn't know that, and the bank thinks that they actually have a credit score of 600. So if there's some kind of systematic underestimation of this nature, we call this like a measurement error. So what does measurement error do to sort of the delayed impact of fairness criteria? So first, we can say that when the scores of a group are systematically underestimated, their acceptance rates will be lower than when their scores reflect the true probability of repayment. Right? And intuitively, that's because if I think that everyone is not going to repay their loans, right, and then I will accept fewer people from that group. And then this fact is also true if we apply a fairness constraint. So even under fairness, having this measurement error will make the acceptance rates lower. So there's something interesting that happens here, which is if we apply utility maximization knowing the true scores, then we would be at this point, right? But if we didn't know the true scores and we use like these erroneous scores for the disadvantaged group, then we will actually be using beta error. And that's in the relative harm regime. So that's doing worse than if we knew the true scores. And same for demographic parity. Maybe the true demographic parity puts us in this relative harm regime. But then because of the measurement error, we only, the algorithm tells us to choose a threshold here. So that is actually giving us relative improvement. So now if we compare the utility maximization acceptance rate and the demographic parity acceptance rate, now you see that the demographic parity acceptance rate gives you relative improvement over utility maximization. So this is a particular setting where it makes sense to use a fairness criteria that will over-accept a little bit, because you're making up for the measurement error in your scores. So if there is reason to think that there is measurement error and you're systematically underestimating a disadvantaged group, then there are situations where the demographic parity is actually doing something useful by over-accepting. But in general, then this also depends on what the fairness criteria is doing in this situation. So like we also saw that equal opportunity could end up loaning less than maximum utility. So it's more of using this framework to look at what happens in your particular situation. So, so now that I've talked about some of the theoretical results, let's look at some of the experiments that we did on real data that also corroborates these effects that we talked about theoretically. So we did experiments on these credit scores. There were like 300,000 of them. And these are meant to predict default risk, as we know. So we just took out the scores for two different race groups, black and white. And we used the empirical data that we have in this data set from TransUnion to estimate the group score distribution, the repayment probabilities, and the relative sizes. So if we look at this score that we get from real data here, we can see that it does satisfy our monotonicity assumption, which is that when you have higher scores, you have higher repayment probability. So this does fit our model assumptions. But there are some things that we cannot estimate from the data, which is what is the bank's profit-loss ratio, and what is the delayed impact when you repay or default. These are not things that we were able to estimate from this data set, but we just plug in some numbers that put us in the regime that we're interested in, which is where the bank is more risk-averse and more conservative. So with these parameters, we then run our model and we compute the outcome curves and look at what is the delay impact under different fairness criteria. So first, we can just plot the outcome curves for the black group and white group. And this just tells us at each acceptance rate what would be the average score change in that group. And it's something we can compute because we know the distribution of scores. And now, what does, say, utility maximization do? So in the bottom part, I'm plotting for you the acceptance rate on the x-axis and the bank's profit. So the orange curves tells you what is the bank's profit at each acceptance rate. And of course, the bank wants to maximize acceptance rate in this case, so it just picks the maxima of those curves and says that's the acceptance rate. And in both cases, you see that it's putting both groups in the improvement regime, so their scores do both increase. But if we do demographic parity, we enforce that both groups must have the same acceptance rate. Then, although the white group still is in this improvement regime, the black group actually experiences active harm. So if we look at another fairness criteria, that's another threshold that it will recommend, that leads to improvement for the black group. So it's what we expected earlier given the theoretical results, and we also see this in our simulation. And part of the reason why the outcome curve is useful is that it helps us kind of tease apart why is it that the minority group is more susceptible to the changes in fairness criteria. So the difference in delayed impact for the black group is clearly larger than that for the white group. So if we just change the fairness criteria, for the white group is the majority group, and it does not see too much of a difference in what their acceptance rate is relative to the black group. And that's because there's more of a misalignment in the curve between the curves on the top and the curves in the bottom panel. So when we switch the fairness criteria, that changes the threshold that's recommended by a lot more for this minority group. So this is one reason why we want to look at whether we want to explicitly model the delayed impact so that we can compare that to what's happening when we are maximizing the utility. So what I've shown you with this talk is that the outcome curves we developed in this paper, they provide a way to deviate from maximum utility while improving outcomes. And in particular, we can think of it as a way to audit what happens when we apply a fairness criteria. And it really tells us that we need more domain-specific models of how people are affected by algorithms. Because if we chose a single fairness criteria and we applied them to all situations, you can already see that it's a bad idea because a priori, you don't know what is going to be the impact of that decision. And in a lot of situations, we see that causes harm to some population under like just a very simple model. So we believe that in like fairness, when you talk about fairness questions in machine learning, we really need to consider the context of the application. So there's also a lot of future work in this space. So we consider binary decisions. You might want to also think about what happens if my decisions are like there are many different interest rates and there are more like a higher dimensional decision space. And also another important question is how should we be measuring delayed impact? What are the other ways of measuring delayed impact that might be more suited to your application? So here we use the mean score, but we might also want to think about individual impact or the variance of the impact or other things like that. And lastly, I just want to maybe draw attention to some of the other work in this space that study like dynamics of the impact of machine learning algorithms. So sometimes there can be feedback loops when you apply the algorithm and then you change the distribution of your data and you use that data to train your algorithm again. So these are like pretty much open questions. How do we deal with that kind of feedback? And there's some work that also look at this question from different points of view. So yeah, with that, thank you very much, and I'll be happy to take questions.
I guess because you're looking at temporal effects, right? So the delayed impact. So in the beginning, at least, you don't have that feedback right away. So what are some tips that you can give us in industry that can get us started as we're waiting for more data?
Yeah. So like that's a great point. So in our paper, we are not even so we are looking one step into the future. So in the sense that we're not taking feedback from the future yet. So I think like one way to incorporate this like look forward thinking in terms of impact is to explore how you can develop models for how your users are affected by the algorithms, right? So in some cases, like for example, credit score, there's a way to like model how their financial health is going to change in the future. But maybe in another setting, you might want to say like, oh, how does their user satisfaction change in the future? And it's nice to start paying attention to how your algorithm is changing that like satisfaction score, for example. So the reason why we want to be looking at those things instead of just applying a fairness criteria is because we don't want to ignore the fact that the application affects people in different ways. So I think that's that's something that is like an ongoing conversation as well. Yeah. Yes.
On top of those elements is because you kind of look in the future and you kind of predict something is going to happen to impact that your model, right? So what is we looking back is what kind of potential, what kind of parameter, or what kind of feature you should introduce before you even deploy this machine learning?
Sorry, do you mind repeating your questions? You're saying what kind of, yeah.
From your research here, you kind of look in the future. You already know there's a possibility of skew of your machine learning already.
Yeah.
Or the impact of your machine learning, which will be delayed. If you know this is going to happen, is there any way you can do it in advance to prevent that happen, or prevent that gap?
Yeah.
In that big jump of the arrow in going to predict.
Yeah. So for example, if we have ways to model the outcome curve, like if I had a way to model the outcome curve accurately, I can say, okay, if you were to run this model, then it put us at this point in the outcome curve, and that's not something we want. And then maybe we can try other models. That's one way of doing it. Or if you were to really trust the outcome curve, like if you think that you have a really good outcome model, then there's also a way to just optimize for outcome directly. So in the paper, we talked briefly about how you might do that, but that's like a simple optimization problem. So instead of optimizing for the profit, you might want to just optimize for outcome. And then, but then there are also other problems that come up. Maybe you don't want to lose so much profit, and you want to make sure you improve the outcome without losing so much profit. Then there's also a way to do that, and also a constraint optimization problem. But I guess like it depends on the business, like how much profit they're willing to lose to make sure the outcome is not like to improve the outcome of their users, for example. And that's maybe like a trade-off that like is left to the person who is implementing the algorithm. Like you have to select that as a parameter, for example. Yeah. Okay, thank you.